So let's continue with pipeline control. So it's my first time reading the book, and the name of the book is Computer Organization and Design. It's the ARM version of the book. Let's begin. Uh, so this diagram is pipeline data path. In this they have included the control signals. The red color lines you can see are the control signals. Yes, and it checks whether the branch is mm, the conditional branch. If it's a conditional branch, then we are gonna calculate the address by sign extending the immediate field, and then we're gonna add it to the current program counter, which is then transferred to the PC again. This loop goes on until the program execution is completed. Then we have this register lock, which is used to switch between uh, if we have R type instruction, or else we have load store instruction, or we have branch instruction. So this is for that reason. This is register write, which tells this register block to whether to read the register data or to write. I think that's clear to you guys. Um, then we have ALU source. This is basically to switch between the incoming sign extended. If it's a load store instruction, a load or branch instruction, basically, then we are gonna use the sign extended version of the immediate field, and then we are gonna add it to the register address. Or else, if it's R type instruction, then we are gonna take the the data from second register, or and then we are gonna add it, and we are gonna store it in this xmem pipeline register. And this is mem read and mem write. Basically, they will be set when we are gonna reading and writing the memory, mem to reg. I hope this section is clear. Let's move ahead. So basically, they have divided the control lines, analogous to con- uh, the stages. Basically, the instruction fetch. It doesn't have any control lines, as we know, but in instruction decode or a register file, right? We have uh, to switch between the register or the uh, or the RT field of the uh, load or store instruction basically. If, so there we need reg to log control signal. Uh, in short, we are gonna have reg to log in this register instruction decode stage. Next, signal selects instruction bits or this 0 to 4 RT is nothing but the it's for um, R type instructions. Um, if I am right, uh, let's verify it with AI. Let's verify it once because I'm pretty unsure. I don't memorize the register values, to be honest. Okay, so it's clear. Instruction decode this stage or instruction stage or pipeline stage, we can say. It uses 20 to 16, which is RM field of the instruction. Basically, it's it's present in the class R type instruction as said, as we verified. And this is from the load or store or the branch instruction. And in execution or address calculation stage, we have two control signals, which is ALU off, which decides the operation, and ALU source, which decides from where we are gonna uh, take the input data. If it's from the immediate field or if it's from the register file, it depends on that. Uh, so there are two control, control signals in this stage. And moving to memory access, we have a branch, memory, and memory. These are the three control signals in this stage, and I hope it's pretty straightforward. I don't think it needs any explanation further. Moving to write back, it has one control line which is mem to rich. That's it. Which decides which data to write, whether coming from ALU or the memory or the data coming from the memory block. they have elaborated a bit on this tiny important thing. Basically, the 28 bit of the R format instruction is set when the instruction is either, the instruction is R format, or it's not set, or it's zero when it's not R format. So it's R format means basically add, subtract, or and these type of instruction. And if it's not R format, which means it's either load store or branch instruction. And whether we can decide uh, a reg to log multiplexer. It takes input of that 28 bit from the instruction to switch between the registers, whether it comes from R format or load store. So they have that's pretty interesting. Let's move to these diagrams. See what these are the instructions, and this is a loop which decides the type of operation we are going to perform. In load store, we are going to perform add operation. That's why it's 00. And I don't know about control and branch why it's 0. I just forgot which operation it maps to. We have R type instruction. Yep, they have given here. My bad. We have load instruction, store instruction, store register. Basically, through the opcode field, um, yeah, this is to decide whether uh, it's the type of instruction we have. If it's an R type instruction, we have 0 1. I hope so. It's like this. And if it's compare and branch on 0, then it's 0 1. And if it's load or store, it's 0 0 from this. It decides the AU operation. And let's moving to the opcode field. See, by default for load and store instruction, the desired ALU action is add, as we are just adding the immediate feed to the base address of the register. and, and compare and branch instruction, we are just passing uh, the input B, which is nothing but the address or base address. And then these are the opcode field for whether it's add, subtract, and or all. And based on this, we have some ALU control unit which controls. If it's an add, we have 10. If it's pass, then we have 111. If it's subtract, and this is all. It's clear, but it's a bit confusing for me. Then why is ALU off? It's just to distinguish between the type of instructions. And why is this opcode? From this we are deriving ALU op. And from this field we are getting. Okay, I hope it's clear to you guys too. Let's move to the next table. Yeah, it's just a copy of figure 4.16 was previously given. So we are once again go through it to just refresh our memory. Let's move to another table. So it's just the control lines. They have displayed the behavior of the control lines based on the input instruction. So it's similar to the previous figure they have mentioned, but they have been so here are the control lines as they have mentioned about they have divided the control lines into these five subcategories. Uh, and in this table, it's just clear we don't have any control line in the instruction fetch stage. So there's uh, the it starts from instruction decode stage and moving to execution stage, which has three control lines, and then moving to memory access stage, which again has three control lines. You can read it here, and then write back stage. So this is how the control lines organized the instruction, then the goes through the control, and basically three of the control lines are used in IDEX stage and the rest are passed. So this happens. It's like this. Let's move on. So, so my target for today is to reach data hazards, and in the next video we can begin data hazards. But let's not rush. Let's clear things. Let's understand the logic behind it. That's my main purpose. don't want to skip things to move on faster. That's not the. That's not why I started. So this is some elaborated data path diagram. As you can see, the pipeline data path controls significantly the control ports of the pipeline registers.